Okay, this is the screencast solution for Digital Logic Exam 3 Review Problem 4. Okay, so it's a straightforward problem because we're just trying to do a one-shot design for the state machine shown. So let's get started. I think the first thing I'd like to look at is state S0, and of course what we need in a one-shot design is a flip-flop representing each state. So let's let this be the S0 flip-flop. Of course we need a clock. Okay, so what you'll notice is there are two ways to get to S0, at least. Turns out in this case there's three. So we're going to put some AND conditions here. I happen to know there's three ways to get to S0. So I put three AND gates. All right, so the first way is I can get to S0 from S1. All right, and so my logic condition for that is AC. All right, so what I would do is I would put the condition first, S1, and because it's AND, I can leave it on to this AND gate and have A and C show up here as well. Okay, the next path to S0 is a little more complicated because the logic is more complicated. So we get from S2 to S0 on this reasonably complicated compared to the others logic expression. Okay, so what I'm going to do is I'm going to put that one, looks like it'll fit right here. Here's S2, and I'm going to make the logic function. This is just a simple sum of products. Okay, so here's my sum of products, and I have the condition A bar, B bar, and C bar, along with A and B bar. Okay, so that's my logic function implemented in hardware that I need. And I'm going to drop that in, say right here. Try that again. And extend this to the gate, and that gets there from S2. Okay, so hopefully you see how that works. All right, and let me clear that. The next thing I want to do is figure out how you get to S0 from S0. Okay, so to work that for this situation, let's switch the color to yellow, and note that we're looking for things leaving S0 at this point. Okay, so there's something leaving S0, and there's something else leaving S0. Okay, so I look at the logic functions on from S0 on an A, right? A, B, and C. On an A, I go to S1. Okay, so that would put S1 here. All right, on that side of the map. Okay, from S0, I go to S2 on A bar C. So that's right here. And those are the two conditions leaving S0. So what's left over means I stay in S0. Okay, so the logic condition that I need to add includes this circling. Okay, so that circling is A bar C bar. It spans B. Okay. Let's clean this up a little bit. Okay, so that's really the solution for the S0 flip-flop. We need to do the same thing for S1 and S2. Let me make myself some room to do that by moving these down further on another page. Okay. All right, so let's now consider S1. Okay, let's change the marker color to purple. We're looking at S1, so we're going to need a flip-flop to represent that state. All right, and it looks like there's only one path leaving S1. All right, so at this point we'd probably want the first thing we need to do is find all the conditions that arrive at S1. And so using my purple marker, I was getting the direction wrong. We arrive at S1 from S0. Okay, so we know there's at least that case. S0A that will get us back to S1. Okay? But I'm wondering, is there a way to get back from S1 to S1 from itself? So that's why I need the Carnot map. And that's where I pursue things that are leaving S1. Okay, so I'm going to use a green marker for that. So I see there's two things leaving S1. I need to put both logic conditions down for that. Okay, so you see on a C bar, I go from S1 to S2. Okay, so S2 goes here, 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 and here. Okay. On A intersected with C, all right, so that's the region, this region here. A intersected with C, I go to S0. So that means anything that's left over is S1. Okay. So let me relocate this so we can put the logic in. What this tells me is I do need an OR condition. From S1. This logic here is A bar C. So this would be A bar and C. Okay. And then we already know from S0 on A, I go to S1. Okay. So all of this takes care of the S1 flip-flop. Okay, so I'm going to group all those together and move them down further on the page as well. Sorry, trying to put this in place where I can have some room to write. Okay, now we need to take care of the S2 flip-flop. All right, so we'll go with orange for that. Okay, using the process we know about, here's a D flip-flop, here's the clock. Here's S2. We look for all the ways that we can get to S2. All right, so you see we can get there from S1, and we can get there from S0. And we'll have to check on whether or not we can get there from itself. So in the meantime, let's put the logic in for getting to S2 from S1. You get there on a C bar. Okay. To get to S2 from S0, the logic is A bar C. Right? So then we just need the kernel map like we did before for all the conditions leaving S2. We want to find all the next states for S2 based on the inputs. Okay. So I see I leave S2 on this complicated logic expression path. It's not that complicated. We could put in that. So A bar, B bar, C bar, that's this square. That's going to go to S0. All right. And then AB is the next term in the sum of products. So AB bar. And so AB bar, is also S0. Okay, so those places on the map are the S0 places. Okay, so that's one of the conditions leaving S2. You see anything else leaving S2? Looks like nothing else leaves S2. So that means the S2 returning to itself conditions are just what's left. Okay. All right, so I need to make a circling that covers all these conditions. Okay, so there's a grouping of 4 here and a grouping of 2 here. All right, so if I read that condition, give me some room to put this. Hang on. I have a condition for returning to S2 from itself, and then I have logic expression. This logic expression in orange would be B or A bar C. All right, so that's a sum of products, and so I need an OR gate here with B, and then A bar C. Okay, so that finishes all 3 of those. Possibly on an exam I wouldn't ask for all 3 just because it takes so much time to go through everything on that. All right, but there you go. That's the solution to problem 4.